It's a problem that has been puzzling the physics community for more than 2 decades. How can we classify exotic hadrons? According to the conventional quark model proposed independently by Gell-Mann and Zweig in the 60s, hadrons are composite particles, which can be categorized into mesons that contain a valence quark and antiquark pair, and baryons that are made up of 3 valence quarks. This model has been quite successful in describing hundreds of hadrons, supported by the available experimental observations for over 60 years. However, more and more recent experiments are providing evidence of new hadrons that cannot be explained by this model. These are known as exotic hadrons. For instance, there can be multi-quark states made up of more than 3 quarks, and also hybrid states, such as glue balls. Due to limited experimental data, physicists employ a bottom-up approach to study exotic hadrons, wherein we start with available data and use a scientifically grounded model to extract the physics. These exotic hadrons usually manifest as peaks in the scattering amplitude or invariant mass of a system that can be measured by experiments such as the LHCb. The dilemma now is that multiple models can be used to explain the data, but provide very different interpretations for that exotic state. A hadron with a 5-quark composition, for example, can be interpreted as a compact pentaquark or a hadronic molecular bound state between a meson and a baryon. To complicate things further, there is also this purely kinematic rescattering mechanism that does not produce any new hadron but can also explain the enhancement in the amplitude, known as the triangle singularity. In our study, we designed a neural network model as a classifier tool to learn and distinguish the line shapes arising from these different models and select the most likely model that explains the experimental data. This framework, which we call model selection, can provide us better intuition towards the interpretation of these exotic hadrons. Hi, my name is Darwin Alexander Ko. To learn more about this work, I invite you to join me in my undergraduate thesis defense this August 7 at the National Institute of Physics. See you there!